Have you ever wondered why uranium arouses so much fear and at the same time incredible curiosity? When we mention uranium, images of atomic bombs and nuclear power plants immediately come to mind. And let's face it, that's not exactly good propaganda. But here's something that might surprise you. Uranium is fascinating. This metal, which occupies place number 92 on the periodic table, has exactly 92 protons and 92 electrons. And look how curious it is. It is 40 times more abundant in the Earth's crust than silver. But why is it so common? Uranium comes from the stars, literally. It is formed after stellar explosions, known as supernovae, which are true cosmic spectacles in which new elements are created. Discovered back in the 18th century in Germany, uranium was named after Uranus, a planet that had just been discovered. And here comes an intriguing detail. Any atom with 92 protons is considered uranium, but the number of neutrons can vary. This brings us to the world of isotopes, which are like versions of the same element, but with slight differences. Some of these isotopes are radioactive, which means that they can disintegrate, releasing different types of radiation, alpha, beta, and gamma. Now, you should know that uranium has 28 known isotopes, but only 3 occur naturally: uranium-234, uranium-235, and uranium-238. And those numbers that look like passwords, they represent the sum of the protons and neutrons in the nucleus of the atom, and yes, they are all radioactive. So why should we care? Well, each isotope has a story to tell, and understanding these differences helps us explore both the risks and the incredible potential of uranium. From generating clean energy in nuclear power plants to studying the formation of our own planet, uranium is at the center of many important discussions. Have you ever stopped to think that the secret to eternal youth may lie in atoms? Yes, I'm talking about radioactivity and a concept called half-life. Imagine you have 1,000 radioactive atoms. After a certain time, known as half-life, half of them, or 500, would have turned into something else. This time can vary from the blink of an eye to longer than your favorite series has episodes. We're talking milliseconds to millions of years. Now let's focus on the star of radioactivity, uranium-238. It's the most common type of uranium on Earth, accounting for around 99.27% of all uranium out there. And guess what? Its half-life is more than 4.5 billion years. That's right, billions with a B. To put it into perspective, that's roughly the estimated age of our planet. This means that since the Earth was formed, only half of the uranium-238 originally present has disintegrated. Did you know that we use uranium to date rocks and even dinosaurs? While carbon-14, our old acquaintance from science lessons, helps us date younger objects with its half-life of 5,700 years, for the real elders of our world, such as dinosaur fossils, we need to call on uranium-238 for the job. Now, let's be clear. Finding pure uranium out there is about as likely as finding a telephony that still uses dials. In nature, uranium hides in rocks like pechblenda, a mineral as dark as the mood of someone who wakes up before the alarm clock. And even this rock is only 88% uranium at most. But what if, in a stroke of luck worthy of a movie, you found uranium-238 in its purest form? What would happen if, driven by curiosity, you decided to touch this material? First, a surprising fact. Holding approximately 2.20 pounds, approximately 1 kilogram of uranium-238 would put you in the company of 12 million alpha particles being emitted per second. Sounds like a lot, right? But the truth is that this represents only around 70% of the radiation we naturally receive every day, thanks to Mother Nature now. Before you think about taking a piece of uranium home as a souvenir, here's a tip. The greatest danger lies not in touching, but in eating or breathing that uranium. Yes, because contrary to what you might think, it's not a new exotic flavor for dinner. Alpha particles, despite being blocked even by a sheet of paper, become real villains when they enter our bodies. Inhaling uranium is not like smelling a freshly baked pizza. That would put these particles directly into your lungs, increasing the dose of radiation to levels that are definitely not on anyone's menu. Uranium, like lead, is a heavy metal. This means that it is toxic to us humans. But wait a minute, you might think. Do I eat and drink uranium? Well, in a way, yes. Uranium is naturally present in the environment, so in a tiny way, it ends up in what we consume. But calm down. Before you start searching your kitchen for uranium, the amount we ingest naturally is extremely small. To give you an idea, the Center for Disease Control, CDC, states that up to 30 micrograms per liter of water is acceptable. Just imagine, you go on a movie adventure and discover a secret source of uranium. But wait a minute, it's not just any uranium, it's the coveted uranium-235, the star of nuclear power plants and atomic bombs. Now, I know what you're thinking. Why don't they use uranium-238, which there's plenty of? Uranium-235 is rare, almost like finding someone who refuses a slice of pizza. Only 0.7% of natural uranium is this very special isotope. But why is it so important? In a nuclear power plant, the magic happens when neutrons are absorbed by this uranium, splitting it in two in a process called nuclear fission. And doesn't uranium-235 love this attention? It is about 600 times more likely to split than its brother, uranium-238. So, to make our power plants work and not just decorate the landscape, we need uranium-235 in a slightly higher concentration, between 3% and 5%. It's like adjusting the seasoning of a recipe to get it just right. Now, if you think that's radioactive, pure uranium-235 would be like putting chili peppers in your eyes. We're talking about radiation almost 100 times greater than natural radiation. But what if by some cosmic chance you enriched this uranium to 100%? Not only have you created something extremely powerful, you've also secured your place on the world's most wanted list without even having to post a viral video. The rock called Pechblenda is not just any rock. As well as containing uranium-238 and uranium-235, which in themselves are quite interesting, it hides an even more curious secret. The byproducts of the decay of these uraniums are even more radioactive. Now, imagine the scene. Marie and Pierre Curie, two of the scientists who left their names in history, were in their laboratory at the end of the 19th century, fascinated by this dark rock, and thought, if this rock emits more radiation than uranium itself, what else could be hidden here? And didn't this curiosity lead to discoveries that would change the world? At a time when radioactive was not yet a word in our daily vocabulary, the Curie couple managed to isolate an unknown metal from the Pechblenda rock, a neighbor of bismuth in the periodic table. In honor of Marie's birthplace, this new element was named polonium. Yes, polonium, not to be confused with Poland, the country, although the inspiration comes from there. Can you imagine if we started naming elements after our favorite vacation destinations? But the story doesn't stop there. In the same year, Marie and Pierre made another extraordinary discovery. Radium, an element that glows in the dark and is 1.4 million times more radioactive than uranium. Yes, you heard right, 1.4 million. To put it in perspective, that's like comparing the light of a candle to that of the sun on a summer's day. And as every great discovery deserves recognition, in 1903, the Nobel Committee looked at them and said, "Here, take this Nobel Prize in Physics for your work with radioactivity." And it didn't stop there. Marie Curie, the superstar, went on to win another one in chemistry in 1911 for her work on isolating radium. Seriously, how many people do you know who have won 2 Nobel Prizes in different fields? Let's imagine you were out walking and found a hidden treasure, a handful of 5% enriched uranium, just like the stuff they use in nuclear power plants. But before you start planning your own power station, let's get a few things straight, shall we? First, let's get down to basics. Alpha radiation. Yes, the kind that a simple sheet of paper can stop. But why do nuclear power plants have gigantic concrete walls? The answer is as intriguing as that episode of the series you can't stop watching. When uranium is used in nuclear fission, which is basically when it is split to release energy, not just one or two new elements are created. In fact, it's like a party of atoms where the sum of the protons has to be 92. But the possibilities for combinations are many. Many of these new atoms are super radioactive, much more so than the initial uranium. They emit all kinds of radiation, alpha, beta, and gamma, with varying energies and half-lives that can range from seconds to thousands of years. But then you ask yourself, why bother if the radiation from a bit of uranium isn't that high? Well, even though the direct radiation from enriched uranium may seem low, don't be fooled. The products of this nuclear party, also known as radioactive waste, are like the guests who stay late and cause chaos. They are the reason why we have so many precautions and, yes, huge concrete walls at nuclear power plants. What about radioactive waste? Ah, that's an even bigger problem. Imagine trying to get rid of something that not only glows in the dark without needing batteries, but can also increase the risk of you becoming a superhero, Reed, causing cancer, if you stand too close. It's not exactly the kind of garbage you can leave on the curb for the garbage truck to pick up. So here's the tip. Unless you want to become a comic book character with dubious superpowers, it's best to leave the uranium to the professionals. And remember, the next time you think about heavy metals, you might want to stick to music. I hope this conversation has piqued your curiosity and maybe even brought a smile to your face. Remember, uranium may be part of many innovations and discoveries, but with great power comes great responsibility. See you next time.